Okay, this is the lecture that covers section 3.0 and 3.1. Jupyter notebooks are on the way. This is for the lecture for the date Tuesday, September 15, and also Monday, September 14 for some of you. So the first part of the week, this is week number 4 on our semester calendar. Well, anyway, section 3.0 and chapter 3 is called Examining Distributions, and so we have a very brief introduction. The heart of the matter today is 3.1, and we start off with variation in the real world, which is by samples converted into variation in data, then distribution, which can be considered complicated, but I don't think it's that bad. And it's a lens through which we view this variation. Maybe it fits a bell curve or something along those lines. So anyway, most people don't understand it all at once. If you find it difficult or vague, don't worry. It'll be a major concept throughout this course, and we'll talk about it. It does ask us to think abstractly, though, at a higher level about your data. So we take away a focus from the individual values up to the entirety of all the values and call it say a normal distribution or something along those lines. A sample of 20 people, for example, you can't just use that as being the numbers for everybody in the country or state or whatever. 20 isn't enough for that. But you could examine the distribution of the height and the distribution of the weight. And what they're trying to get at is you were somehow going to combine them together, height, weight together. That wouldn't make any sense. Like you add them up, that would be kind of pointless. There is a body mass index, but that's not really the same thing. So you would want to keep them separated. If I was making a different point, I suppose, with the small sample size, you can't really get a lot out of that. But data are typically inherently complex, and even a small data set includes a lot of numbers and lots of variation. So we use the idea of distribution, and we want to see, well, all the variation of the characteristic of a single thing, such as the whole is greater than the sum of its parts, forest, the trees, and all of that. So they have a kind of a question here. Let's flesh out this analogy between individual measurements and a distribution. So which ones are distributions, such as forests, and which are individuals like trees? And yeah, looking at the student views, I don't really tip my hand here. It's meant for you to kind of guesstimate at it. But, if you've got one person, that's clearly a tree. If you have, all the nations in South America, that could be considered to be more of a distribution. But you just kind of sort it out for yourself. They'll give you what they think the answers are right after you're done. And they also have more of the same thing. Average happiness of all countries, that looks like that might be a forest. And an individual student, that could be a tree. But, just see if you can go through that. So anyway, the features of a forest can't be seen in a single tree. This isn't going to happen. But when you get to a forest, there's several values put together. That's a whole different thing. You could, check it out once you get enough measurements. But the mean, what they're saying here, statistics such as the mean do not themselves constitute a distribution. That isn't really enough. They're features of a distribution, and individual trees would not be susceptible to that. An average would only be an average, and that would be where the trees tend to go, like the average height of the tree. Most trees will not be the same as the average, but we want to look at the group versus the whole. So let's go on to the next one, and it doesn't let me go to the next slide, so let's just punch it out through the usual way. And modules will let me go there. Okay, so let's go to 3.1, and that's the heart of the matter today. See how far we can get through this. Visualizing distributions with histograms. They're like special bar charts. So there's a host of tools in statistics that we can use for exploring distributions. And many of these are visual pictures. Pictures worth 1,000 words, as they say. We've got histograms like these are, box plots, and other types of graphs that we'll talk about. And being skilled is really helpful. It's an important part of the toolbox, they say. It's something you can take with you. And we could take a look at some of the distributions of variables, and we're not really getting a lot out of it yet. We're just taking glimpses as to what happened in these 4 cases, like the ages of housekeepers. The ages range between around a little less than 20 and a little more than 60, but here are the counts on the other axis, the y-axis, and here's 8 of them that land just shy of 30. That's a very popular number. Don't have anybody who's 60 years old, for example. And the thumb length of students' fingers. Well, you've got the thumb length, which could be as low as around 40 millimeters, I guess, and then up to 90, along with the counts that range up to almost 25. So looking at the scale is very helpful. So if I can zoom in a little bit. Life expectancy of countries on the Happy Planet Index. Now, they've not listed the countries, but we can see that some countries only have about 40 years, and some have about 80. And the top 6 in that head command, we saw, I think it was Angola and Australia, that had quite opposite life expectancies. And so that's kind of spread out, and 70 is a very popular one. But there's a wide variety depending on what country you're surveying. Okay, we also have the population in millions of countries. So here's, well, this is kind of a rounded number to need some explaining, but if you get to half a billion, I should say, 1,000 million, those that say millions here, is a billion. There are 2 countries that stand out as being over a billion, China and India. I can't remember which one's number 1. I think India's number 1 or China's number 1. Either way, there's only one of those, each of those. And then you've got some of the more bigger countries like the United States and others, but most of them are closer to 0. Over 100 countries are close to 0. Now you'd have to parse it out and see what the length of each of these histogram bars are, which they're not giving you right now. So the question was, which axis represents the variable in these histograms? Well, I'll let you answer that one. But there is a count along with what we're talking about, say thumb and population. And they have some others. I shouldn't really go into too much detail here. You only have a certain amount of time, and you can kind of read these and guess them for yourself. And once you make a guess, you'll see what the answer was. And no harm done. The idea is to give it a try and see how it goes. Okay, so we have frequencies there. And now we get into a little bit of the programming here. I think I've got, now I need to squeeze it down a little bit more. Make it a little less readable so I can fit everything on the page. And I can expand it just a little bit. It takes a little bit of tinkering where I get to that. A little bit too much. It's really hard to get that fine line going. I apologize for wasting your time. Okay, so one important thing to know in the histogram is that the y-axis, up and down, represents either the frequency of some score or a proportion of a sample that had some score. So in the first histogram, the height does not represent how old the housekeeper is. That was along the x-axis, back and forth, the left and right. But it represents the number of housekeepers, as we mentioned before. So they have a command called GG formula. They didn't tell you where it came from. It's just what they decided to pick. So not easy to remember, I guess. But then we also have GF as a formula command. So we'll be talking about, we don't really care about this part too much, but we do have GF underscore histogram with something in parentheses, and that's basically a histogram command. And we have inside the parentheses the tilde. That goes over an N in Spanish, as I'm sure lots of you know that. And we have pequeño, for example, other words that have the tilde on the N. And data is equal to fingers. That comes from the data set. So that's just something we have to say. So let's go ahead and run this code, see what happens. There was no hint here. It just says, let's run it. And, well, it's taking a little time there. Finally, it pops up. And you see the thumb lengths. This is something we've already just looked at. And we actually have a better view down here. Let's take a better look over here. It's the same graph. It's just not as squeezed as the other one was. I was really shrunken down. But it's the same information exactly. Very popular thumb length looks like around 55 or so. And in the 59, 55, 60 area, a little bit past maybe 65 is also a very popular one because you get around 20 or more that have those thumb lengths. So notice that the outcome variable thumb is placed after the tilde, typically in R. Whenever you put something before the tilde, it's got to just go to the y-axis. And if you put it after the tilde, it goes to the x-axis. So y goes to x. So let's see. If we want to change the x-axis, let's put it where it belongs at the second spot where the x-axis would go. and we can kind of submit that and see what happens. And thinks about it. Yeah, we've got a green. A green is good, so we have success here. They did not give us the other data, so I found this a little unclear when I first ran through it. So I'll just give you a little bit of free information on that one. They did say it's the x-axis, and that's what they hinted up here. Y-axis first, x-axis second. So it's not very important in statistics, but they say it's fun to change the colors of a histogram. I was kind of stressed during the summer trying to get this stuff done, so I really could not care less what color it was. And they do have lots of colors. If you click on the color, I'll just get it off my toolbar if it runs. And so you can see there's a wide variety of colors. There's the first page. There's the second page. There's the third page. All the shades of gray. That's not so much fun. And various other off the beaten path colors like gray 100, gray 96, lavender blush 3. You name it, they seem to have got it, and there's more. All this ones away, you can see there's quite a lot of choices here. So yeah, I think you get the picture on that one. Let's go back to our place. And so now what they've decided to do is to get from the variable thumb and from the data fingers, color will be green. It must be put in quotes. And it'll just frame the outside of the histogram bars. It will not go for the inside, just as the outside. Yeah, that's nice. It has a highlight for you there. And, you know, you can always go for the regular colors, too. You don't have to pick aquamarine or Mally Rose or whatever. You can just pick red, blue, green, and yellow if you'd like. That's typically what I did just to save time. But if you'd like to experiment, you certainly have those available to you if you want to. Has no effect on your grade, unless you just can't read it for some reason. Like you pick white on a white background, that may not work too well. You can also fill in the bars with different colors using the option fill, so that's what that's for. Now it would fill the inside of the bars. So let's take a look at what this would do. They're just going to show you what happens. Notice the outside of these histograms are still green. This is a stark, shocking looking graph, in my opinion. But they had fill with yellow. Everything's exactly the same as before, except we have the fill command. So that's what happens. You have the fill command, and it has yellow inside. The other one had black inside. I guess black may be default. That's just sort of the color they use in general. You can improve the histograms further by adding labels, and you can add a title. Titles are nice, and so we have a new command called GF Labs, I guess, for labels, function that adds the labels. And if you need to connect them, you can put the percent sign greater than percent sign. It's supposed to represent a chain. So it chains them together like it's connected. It may not fit on the same line, so it's often used to connect things that are kind of in the same train of thought or the same line. I'm not sure what would happen if you split them. I haven't tried it, but you can try it if you want. But this one does have, of course, the title, Distribution of Student Thumb Lengths, and it also has the same data as before. This one doesn't have any fancy coloring, however, but it is the same data, as you can see. It has the title, as you can see. Sometimes you may want to change the labels for the axes as well. That can be done. You may want to label the axis thumb length in millimeters instead of just thumb. It's a little bit more precise. But if you don't specify a label, R just puts it in the variable name, which is thumb. So if you just want to make it simpler, it'll do that too. But here in this case, we had to type in after the title, they also said X equals, quote, thumb length, millimeters, unquote. So that's the only change that happened here. So I'm trying to circle with my cursor right there. So now notice how the X-axis has gotten changed. They haven't touched the Y-axis. The count seems to be good enough for that. You could come up with a synonym for that if you'd like. Now change the label for the Y-axis to whatever makes sense to you by modifying the following code. So we could just put in Y equals numbers or totals or something like that. How about that? I'll just put in totals, which is just a little bit different than count, and we'll see if I can run that and see what happens. I may have to submit it since I'm in student mode, but there we go. It does have totals there. A little bit hard to read, but there it is, totals. I'm trying to circle it. And so we replaced counts. The data is still the same. It's just a little bit squished, but if you look at it carefully, you can see it. They still have the same peaks in the same locations as before. It's just that it's been squished. It's a very scientific word, of course. Let's take another look at some other stuff here. So there's a lot of versatility that's available here. Whenever you run across an R exercise, feel free to play around with different options regarding color, fill, or labels. And it also says when the variable on the x-axis is measured on a continuous scale, the bars on the histogram usually represents a range of values called bins. They've come up with a way of calculating that kind of thing. But you can specify what the bins would be. Sometimes they're called class intervals. That's the classical way of saying it. They're calling it bins here, and that's fine. We'll illustrate this idea by creating a simple outcome variable called outcome. We'll put it in a tiny data frame called tiny data. Okay, that's fine. So we can try to do that, and let's see here. What they want to do is read the code that we use to create the data frame, and then we can add some code to create a histogram of outcome. And we could use the arguments color and fill, and we'll see what happens, and we can pick any colors we want. So they don't have a hint here, but what we can do here is type in GF histogram, because they do want a histogram. So GF, and that's underscore, that's like near the hyphen, except you have to capitalize that. And of course, we'll type in histogram, spelling it correctly. And then we'll have to type in with parentheses the tilde for outcome. That's the variable we're using. The tilde is found in the far left corner, at least on my keyboard. And I'll type in outcome, which is not capitalized. And then I'll put a comma, then I'll put data is tiny data. So I'll put equals, I'll put some spaces in so you can read it a little bit better. Tiny data, data is equal to tiny data, I should say. And then we can then fill it with any color you like. I picked blue. I'm not very imaginative. I didn't feel like looking up all the different colors. And so I put in blue, and then you could use the color as, say, gray, or I don't know, some other color if you'd like. How about orange? Let's just see what happens if I type in orange. It may be kind of a clashing situation. So I'll make sure the quote's on there, no extra parentheses needed. So let's just go ahead and run it, and you should submit it when you're satisfied with it. So there it is. We have orange on the outside, a little hard to see. The fill is the inner part of the histogram. The color is the outside part of the color. And you can see now that the x-axis is done in orange, so that's also nice to show it. And we have kind of a boring data set. We have the 5 numbers, 1, 2, 3, 4, 5. That's it. And we have a histogram with 1 in each of the numbers. So outcome number 1 has 1 of them. Outcome number 2 has 1 of them. Number 3, etc. Not very interesting, but it does illustrate how a histogram can be done. It's also a version of the uniform distribution where everything has exactly the same value, such as the last number of a Social Security card that's collected over thousands or millions of people should be approximately uniform, or random number generator, numbers from 0 to 9, that kind of thing. So they pick different colors, of course, as you can see. It's basically the same outcome. The outcome numbers 1, 2, 3, 4, 5, and the counts just as good as totals, is 1 apiece. So not much happened there. They just illustrated different colors. So this histogram shows a gap, or shows gaps, I think that's a mistake, between the bars, because by default, this sets up 30 bins. Ooh, 30 bins. That's too many. So we had all these spaces. We only could fill in 5 out of the 30. Sometimes 30 is a perfect number, so I guess that's why they picked it. But in this case, it wasn't. So we had only 5 possible numbers. So if we change the number of bins from 30 over to 5, because we have 5 numbers, wouldn't that be a better fit? And sometimes you're not really sure what number to pick, and you can experiment. We'll show you a little bit of that later on. And you could pick other numbers, but here it's kind of an easy one, so just pick 5 for the 5 numbers, and then it just fills in all the gaps. The number 1 is there, centered around the 1. The number 2 is centered around the number 2. These look like discrete whole numbered values, and so we don't have to worry about decimal interpretations here. There's enough time for that later on when we get into decimal interpretations. And I'm glad we don't have to waste time with kind of an old-fashioned way of generating these things, which is so often done by hand, and it was very, very tedious. I'm glad to see that's gone. Now imagine this. Say we use the same histogram command with just 5 bins, but we add a new number to our variable. What bin do you think it will go in? Well, this is where I take back what I just said. These are really not necessarily discrete numbers. They could be considered continuous numbers. So the numbers that are close to 3, you can kind of see where the boundaries would be as I kind of point you in the right direction. Looks like that's about halfway between the 2 and the 3 and halfway between the 3 and the 4. And 3.2 might fit around there, which means it would probably be in that bin. But I should let you figure that part out instead of handing it to you. So here what they did was they put the 3.2 in. Notice how the other 5 numbers were still there, and all they've done is they've added in another number. So we can just simply run this. I think the hint just says to just click run. That's my favorite kind of hint. Let's click on this so we can kind of see it, and I'll hit run. And you would want to hit submit once you're happy with the running part. And all it really did was it put an extra value in the 3 area, the bin for the 3s. Essentially all the numbers that round to 3, such as 2.50 rounds up to 3, as you know. But 3.499999, a number just barely less than 3.5, would round down to 3. Excuse me. So they have shown the same graph again on a bigger plot. So you can see the same data twice. And notice how we have 2, count of 2, in the 3 spot. 3.2 rounds into the 3. It's closer to a 3 than any other number. And of course, it's absurd to have a half of a count. That's just silly. That's just unfortunate the way they structured that. If you put it at 3.7, where do you think it would go? Well, you can make a guess on that. And we could even type it in and see what happens. I'll put in a comma, 3.7, and we'll see what happens with this. And we'll have to change the bins. Well, actually, I won't change the bins. I'm going to leave it alone because we've got 7 values. We had the original 5, the 6th value, and now the 7th value. All I have to do now is just to run this, and we'll see how it turns out. And now you see what happened to the 3.7. 3.7, as you probably know, you better know, that rounds up to 4. So that means it got in the 4 pile, the groups of 4. 3.7 is a lot closer to 4 than it is to 3. So that's where it went. So it's just like saying round this number to the nearest whole number. So that's what we did. Should have gotten some water to drink as I talked. Same picture exactly, just on a different scale. So yes, it went to the 4th bin, which seems to go from 3.5 to actually just a little bit shy of 4.5, but let's not worry about that too much. Now, what if we adjusted the bin width to see how big the bin is? And this time they only picked, well, 4. So we could pick a width of 4, and that's a width of 4. So that's called bin width, not bin numbers, but bin width. So that'll say how big the bin is, how wide the bin is. So we have a length of 4. They somehow picked a 2 as kind of the center mark, and then they decided to go back 4 units. 2 minus 4 is actually a minus 2. It looks a little strange. 2 plus a 4 is 6. So you can see the widths of each of these is 4. And they came up with a way of picking the 2. Maybe they could have picked 3. They just happened to pick 2. That part you do not worry about. The programmers have apparently done that. You could override that with more advanced commands, of course, if you really wanted to. Well, why are there only 2 columns? Well, we just have such big bin widths. The data is spread out, so it just isn't going to work out so well that way. So we have 2 columns with a width of 4, and they do talk about what I just said, going from -2 to 2. And there's only 2 numbers that go into that bin for our tiny set of outcomes. So those are the smaller numbers. In fact, they point at them right here. The 1 and the 2 fit in that first part. I won't say half, but first part of the diagram that came along, the histogram. And then we also saw that there were 4 numbers or 5 numbers that landed on the other side. So that's why it's kind of a distorted looking histogram. You had 2 on the first part and 5 of them on the second part. So that's all it's doing. It's not something that's very useful. It just shows you the comparison of the 2. None of our numbers were negative. It just had to do that because it was put in a difficult position. It had to include numbers as high as 5. So it kind of went to the maximum. And I guess that's how it kind of generated it. And actually went up to 6. So it's a little hard to say exactly how they did that. But do not be concerned about it. They came up with a way of dividing it up into 2 bins. And that's fine. So it's important to note that adjusting the number and the width of bins will change the pattern you see in a variable It's good to experiment with different settings because sometimes you can actually find a histogram that doesn't really represent the data very well because sometimes people have cherry-picked data. It's kind of hard to do. It's not really worth worrying about because it's a bit obscure. So if you picked 80 different histograms to represent the same data, some would look, in fact, most of them would look just like it's supposed to. There might be some other stray numbers that collect in a weird kind of way that don't really look, say, like a bell curve. You can cherry pick a way to make sure it doesn't look that way, but that's not what we want to do. That's not the idea of this class at all. We want to pick a standard length like 10 or something. Pick nice round numbers. Don't pick some obscure bin width or bin numbers or something like that. Just pick 5s and 10s, and nobody will ever question you on that. If you pick 17 or a width of 6.93 or something, then they'd say, why are you doing that? That would kind of tip your hand if you've got some situation that you're trying to convey some agenda, say, to try to impart. Okay, so here, there's a new R window that we could check out, and it says adjust the number of bins to 50. So, of course, obviously, I hope to you, that you just put a 50 there, and we could change the number of bins to 5 over here, but they have not even helped us out with the bins yet. We have to type that in, type in the 5. Now, the bin width is 3. And here we also need the bin width. They have not talked about the number of bins here. They've talked about the bin width, and that will equal 10. So different things will happen as we look at that. I will take a look at the hint. Be sure to set the bins or bin width for all 4 histograms. Let me close that up so it doesn't get in the way, and then we will run it and see what happens. Should have 4 different histograms. I'm going to take them in order. It gives it kind of backward order here. In the first group, we have the thumb data from the fingers data set, 50 bins, so it's all stretched out. And that's not so bad here because we did have a lot of clustering up in the middle. So that sometimes 50 is too many bins to worry about, but it worked out okay here. Let's go to the second one. There's only 5. Now this one, this does not look very pleasing. It's the same data. And yeah, you can see how it kind of groups up towards the 50 and 60 area, but now it's just, you've lost a lot of data. The first one does look a lot better. That is maybe a little bit too much detail. Maybe something in between would have been a good choice, like 40 or something, but the 5 is not very good. If we go to the third one with bin width of 3, that doesn't talk about the number of bins. It just sets the class width, so to speak, the width of each of the box plot. I'm sorry, not box plots, but the bin widths will be 3. So each of these has a width of 3. It doesn't tell you where it starts and where it ends, but one might imagine this is from around 37 to around 40, et cetera, et cetera, et cetera. And this one, you could even count the number of bins if you wanted to see how they line up. I don't really need to do that, but it looks like around 20 or so if you were to count them all up. So it's just a different perspective. If you don't really want to count the number of bins, you could actually pick a bin width. And let's just see what happens when you go to bin width of 10. That's going to be more like the other graph. Now we see 1, 2, 3, 4, 5, 6. That's kind of like saying 6 bins. It was very similar to the second option. The second and the fourth option were pretty close, but not quite the same. They were off by just a little bit. That might imply that the 5 bins had maybe a bin width of 12 or so. And we don't need to get into calculation of range, which is maximum minus minimum and all that. That could be done, but they're kind of doing that for you. And so they have a few questions for you, and I've noticed that some of you pioneers that are on the forefront of all of this, there are about 10 of you that have already done it as of Friday night when I'm recording this, and that would be wonderful, but there were a few mistakes. Now, you're not being judged on the mistakes. I hope you learn from your mistakes. When you see a green check mark, that's what you want to see. Some other color, not so much, and just learn from your mistakes. Maybe take notes or something like that. So when you see clumpy big blocks of data, what happens? And there may be more than one correct answer. If you see lots of gaps between blocks in your histogram, there may be more than one answer. So do your best to try to come up with something for that. So as we get towards the end here, we have relative frequency histogram. It's pretty much the same, except now we're talking about a proportion, which could be easily converted to a percentage, by the way, which occasionally is done. But what they'd rather do is put in a decimal. In other words, 0.10 is the same as 10%. 0.2 is the same as 20%. But they do prefer the decimals, and especially when you're trying to cover huge amounts of data, like in the thousands. then you don't really care about the raw totals so much anymore. You do care about the percentages. Like people want to know on election day what's the percentage of votes for candidate A and candidate B. They don't so much care about the raw totals that is available, but most people would rather see, 59% for so and 39% for so and so, that kind of thing. But they will go to the decimal part. Notice the graphs are exactly the same. This one had the counts. It had 3 versus 4. And it looks like these numbers are off a little bit. I would have calculated that as about 3 sevenths and 4 sevenths, which I believe is more like 43% and 57%. So there may be a glitch there as far as the scale is concerned. So I'm not going to worry about that. But they did ask you to say what similarity said. They're exactly the same distribution. On the y-axis, count versus what they call density or proportion. Better word, I think, here would be the differences, of course. And the x-axis is exactly the same. So relative frequency histograms are useful because you can compare the distributions across samples of different sizes. So say you have 100 in one group and 10,000 in the other group. It's all the same in terms of percentage or proportion. So it'll still range from 0 to 1, which is 0% to 100%. And they say it's not exactly the same as proportion, but for our purposes right now, just think of it as a proportion. Very similar. So we can see what happens with this one. It says we have a new command, GF_D histogram with parentheses. And what will happen is a density histogram. The only switch is you put a D in front of the histogram. That'll convert it to a proportion for you. And I think we can just run this one. Let's see. First line is almost right. Remove the part that makes the first histogram a density histogram. So what we'd like to do is, I think that's actually a mistake because we do want a density histogram. So yeah, so that was a mistake. We do have ranging from, say, 2%, 4%, maybe 6% on top. They did not put that down. So a number that's getting close to 6% shows up. So not only are the counts available, but the percentages or proportions, the density calculation is also available. So near 30 is, has about 6% of the data, but that happens to be one of the biggest ones. So number just shy of 30, maybe 28, 29 for age. And so we can create a frequency histogram of age, and then we could just simply copy this and remove the D. So I'm going to just basically copy this line, stick it down, just right underneath it. How about there? I'll copy it with Command V and remove the D and see what happens. And now I'm going to run it. And it's going to just sort of piggyback onto the other side. I'll look at graph number 2 and number 3. And number 2 is the same as number 1 because nothing happened. But then we go to the next plot, and it's the same shape. You should notice it's the same shape. But now we've got the counts back. Counts are back. So that's what happened without the D. The D says density, proportion. And this one does not. This goes for regular counts. And the D is especially helpful, as we said, when we're comparing different data sets with sometimes vastly different counts. Both significantly statistical. In other words, we have enough data in them, but maybe one has a lot more than the other for some reason. Never a problem. Also, if you can check the console part, yes, we removed a row containing non-finite variables. They do mention this. I'll get back to the plot. And what happened was there was a missing value, missing data point in the data frame. So they let you know about that. They kind of played gotcha with this. And so there's a missing data point. Do not be concerned about it. But this is what we just ran through. Here is the data set with the density. Here's the data set with the count. And they're almost exactly the same. So what differs between the two? Well, go ahead and answer that question. And it looks like we're towards the end here. As you can see, the shapes of the two look identical. Of course, they are identical. Same data points are being plotted. The only thing different is the scale of measurement, the y-axis, mostly because a lot of people would rather look at proportions, percentages, and other times you have vastly big amounts of data or changeable amounts of data, and maybe one on the counts would be very, very short, and the other one would be huge. That's what I try to put with a cursor, and it just wouldn't be like you couldn't compare them. Apples and oranges would not be comparable. But if you put them into density, proportion, percent, style, then suddenly they are more comparable. So we have that, and so in this case, the density histogram looks basically the same. It becomes more important. Density becomes more important to us as we start to compare multiple groups. So it's good to get in the habit of at least knowing how to do it. And And so you should remember the D in the histogram command. Okay, so that seems to be it for today. We're not going to be covering as many sections per day. We do have to get to the Jupyter notebooks. They are now talking. I joined the tail end of the meeting today. I couldn't join the beginning part because I had trouble with my laptop, and I was still working at the tutoring center as well. So I sometimes have to join late. And the gist of it is, looks like they're aiming at the first 3 chapters for the midterm, which will be at the end of the month. There's a possibility we'll be delaying the test again. Looks like the earliest person is having theirs on September 30. So I will be under some pressure, which I don't have a problem with, delaying the test. So it's not an official announcement yet, but it's looking quite likely that we'll be delaying it by 2 more days. So whether you take it on the 30th or maybe the 1st of October, I'll make the official announcement later. So just in case something happens that I do not make the announcement, I'll have to put that little caveat in there. But it's looking like 90% likely we'll be delaying it a little bit because I don't want to be the first one giving the test out. I want to kind of go with the wave of people at just about the same time. And different versions are asking us to contribute to all that kind of thing. There's a little bit of insider information. Okay, so more on the Jupyter Notebooks on the live lecture coming up, but this, of course, substitutes for the lecture on Monday and Tuesday, the 14th and 15th of September. We'll be back live on Monday or Tuesday, the 16th or 17th of September, and then we'll be going a little bit further into Chapter 3, but for sure we'll be looking at some Jupyter Notebooks. I think that's probably best to do that one live, although it doesn't hurt to have a summary on a recorded lecture as well. So that's about all I have for now. Send me emails. The Course Cod is working a lot better than the other thing I have called WebAssign as far as sending announcements. And just keep in touch with me via email. Of course, the office hours, 4 hours on Wednesday almost, so just check in with me there. And stay cool, stay out of the smoke, and have a nice few days here. And we'll talk to you live on Wednesday, Thursday. Bye-bye.